Because there is a plasma in the star, the emitted light of plasma is very bright and very stable, having 10,000 degrees Celsius of temperature. The fuel finishes because of nuclear fusion happening in the star. The gravity pushing downwards and the fusion released energy moves to outward direction. This process keeps the body stable. The nuclear fusion stops due to finish of fuel. This stops the outward push of force. The inward direction force is free to come to the center. The star temperature rise and star becomes small. The star starts to spin. The very fast spin generates magnetic field. The inward pressure pushes the electron in a nucleus, and there the proton captures the electron and transform it into neutron. Due to this exercise, an electron neutrino is released. Because the core is shrinked, the neutron comes closer to each other. The shock wave and wind of neutrino blast the core because the core was more and more forcefully shrinking, turning the core into supernova, having dust and gas in it. This cloud of dust and gas can again give birth to a new star. The star is converted in neutron star where the neutron are stuck together. Two stars orbit each other in binary system. If one star is converted to neutron star, it can continue to orbit its partner. Same way, the planet orbiting a star, but now that star is converted to neutron star. The planet can continue orbiting that neutron star. A neutron star is a very dense object. Multiple suns can be packed in this small area. If the neutron star is more compressed, the gravity will take over and it will turn neutron star to black hole. The surface temperature of neutron star is 1 crore degree.
Due to its small size, it spins extremely quickly.
The surface gravity of neutron star is very much high.
First of all, time is greatly dilated. If astronauts landed on the neutron star, they would only age 10 months for each year that passes on Earth. The difference of pull between their head and their feet is here 100 million times stronger than Earth's gravity. They would instantly get spaghettified. Finally, the neutron star deflects light rays around it, bending the geometry of space-time. Like a black hole, it creates a gravitational lensing effect, distorting the image of surrounding objects, and even allowing us to observe its rear. At the surface, a neutron star is most likely surrounded by a thin atmosphere, no thicker than a human hair, under which lies a perfectly smooth surface as the strong gravity flattens any roughness that would protrude. Under its surface, the neutron star has a crust, mainly solid, made up of atomic nuclei and free electrons.
The gravity and electromagnetism and strong interaction under the crust brings the matter close to each other. The close coming nuclei take the shape of tube, and these tubes are arranged in layers. Even these layers fuse together and no blank space is left. Only some bubbles are there in the liquid of neutron. We see geometric structure with different layer inside the crust, and this is the strongest packet in the universe. The pressure is more in the core of neutron star.
where the pressure is greatest.
The close coming particle repel each other as they don't want to overlap.
This is called the exclusion principle. The form of matter whose structure is governed by the exclusion principle is called degenerate matter.
There is a confusion in understanding the degenerate matter. Neutrons are made up of quark. They are not elementary particles. How they are sticking together? They cannot stick together. Then what is happening?
And one could imagine that under such pressures, the quarks would separate to form a superfluid, or even a plasma of quarks and gluons, whose properties would be exotic.
A magnetic field of 16 Tesla can levitate a frog. The magnetic field of neutron star is 1000 Tesla. You are understanding what I am saying? The shape of vacuum changes with such a strong magnetic field.
Light moving by may be deflected, split, or recombined.
The magnetic field of neutron star exits from North Pole and comes to South Pole, making a ring. The neutron star has a magnetic axis line,
which in most cases is not aligned with its axis of rotation. When it spins, the magnetic field of the neutron star follows this rotation, creating intense fluctuations which propagate at the speed of light. Reasonably close, the magnetic field of the neutron star traps the surrounding matter and forces it to stay near the star. Conversely, at a great distance, the magnetic field varies so quickly that it opens and accelerates charged particles outwards. In this way, the neutron star produces two beams of extremely powerful electromagnetic waves that escape along its magnetic axis. Like a cosmic lighthouse, these radiation beams sweep space periodically and emit a signal whose oscillations pulse metronomically. When Earth is in the way, we observe a tiny bright spot which flickers in the sky. It is a pulsar.
Pulsar has different frequency of oscillation.
The faster the neutron star spins on itself, the faster the pulses we observe on Earth.
Some spin very quickly, at almost 1,000 rotations per second. Most of these very fast pulsars occur in binary systems, orbiting a star.
They are able to accelerate to these extreme speeds by capturing some matter from their companion.
The rotation of a neutron star is extremely stable. Its precision is comparable to that of our best atomic clocks.
The emitted pulsar light has very regular and very metronomic oscillation.
But during the thousands of years of its existence, it slowly loses energy, magnetic energy, and gravitational energy in the curvature of spacetime. Gradually, pulsars lose speed and end up performing only a few rotations per minute. During this slowing down process, the surface of the star adjusts to the centrifugal force, which becomes weaker and takes a more spherical shape. Suddenly, the surface falls down a few micrometers in less than a millionth of a second. These phenomena have the effect of slightly accelerating the rotation of the star. Usually, the populations of pulsars are classified in a diagram, which shows their rotation speed against the rate at which they slow down. We find binary pulsars, which rotate very quickly and are very stable, and slower pulsars, which slow down over time. From Earth, we observe all types of radiation. Most pulsars emit radio waves, but others can emit more energetic X-rays because of their rotation and very strong magnetic field, or even gamma rays. Some of these pulsars have magnetic fields so strong we call them magnetars. They emit powerful X-rays and gamma rays in an irregular way, which makes them very difficult to describe. Today, we know of nearly 3,000 pulsars in our galaxy. Unfortunately, the vast majority of neutron stars remain unobservable from Earth. Most of them have very thin beams that don't sweep our sky, and our current telescopes can only detect the most active pulsars. These objects are still mysterious. They raise astronomical, physical, and mathematical questions that have yet to be answered. But pulsars are of unprecedented interest in the world of astronomy. They can allow us to probe into the theory of general relativity to its most extreme limits, allow us to understand the behavior of matter under such intense pressures. They provide us with cosmic clocks of extraordinary stability, and their study could contain clues as to the behavior of gravitational waves. Indirectly, pulsars could tell us about the nature of dark matter and the existence of primordial black holes. Pulsars are also very good reference points for satellites to orient themselves. And finally, it is around a pulsar that we observed the very first exoplanets.